Take the Kronor.io payment gateway, for example. They've built this remarkably strict authentication pipeline using GraphQL. First, you provision a short-lived API token, then you construct a bearer authentication header, and finally, you execute a post query. But here's where it gets really interesting, their state management. Unless the HTTP transport protocol itself completely fails, their API will always return a 200 OK status code. So, whether your payment was successful or you hit a validation error, that transaction state is bundled right inside that 200 OK wrapper. It essentially forces the client to explicitly parse the payload instead of taking the lazy route and relying on HTTP error codes. But hey, getting through authentication is just step one. Once you're actually inside those financial markets, predicting time series data is the real beast. Historically, standard continuous vector AI models have really struggled here. They treat market data as a continuous math problem, which usually just leads to gradient explosion because of the extreme noise and volatility. The Kronor Foundation model, though, it takes a completely different path. It ditches continuous vectors altogether and uses discrete tokens to map the market's microstructure. It basically treats market action like a structured language made up of coarse and fine tokens. To actually pull this off at scale, the team fed their pre-trained Kronor AI model zoo a staggering 12.1 billion standard candlestick records across 45 global exchanges. And they offer a range of sizes, from a 4.1 million parameter mini version all the way up to a 102.3 million parameter base model. Quants can easily deploy these open source tools to spot sequential patterns across different context lengths. And the results of forcing that continuous numerical stream into a discrete vocabulary, honestly, they speak for themselves. The Kronor framework achieved a massive 93% boost in rank information coefficient for price series forecasting compared to the leading time series foundation model. It's a brilliant solution to a fundamental problem with how machines perceive financial time. So, abstracting time in finance is one piece of the puzzle. But what happens when we shift gears and look at physical execution time across massive distributed server clusters? This is where the Kronor distributed job scheduler comes into play. Built in Go, this architecture is designed for scenarios where you have thousands of jobs firing off across multiple nodes. In that environment, you need absolute certainty about your system state. To get that fault tolerance, it uses PostgreSQL as the single source of truth, meaning it can survive crashes without dropping a beat. It also uses advisory locks for leader election, making sure only one active scheduler runs per cluster while keeping a pool of stateless API nodes that can seamlessly scale horizontally. And when we look at the Kubernetes side of things, the Kronor operator handles FinOps and scalability in a really clever way by directly manipulating the time states of the cluster's resources. By defining a custom resource definition, or CRD, engineers can attach automated sleep and wake schedules to core resources like deployments, stateful sets, replica sets, and cron jobs. You're basically doing time-based resource optimization, literally turning the infrastructure off when you don't need it. Of course, aggressive automated scheduling always brings up a big question. What if you desperately need a resource right now? Well, they built an operational escape hatch for that, called the Kronor CLI. If you're dealing with a sudden security incident or an emergency debugging scenario, engineers can instantly issue a force wake or force sleep command. It completely overrides the automated CRD schedules, giving you back manual control of the execution state immediately. Now, let's peel back another layer and go straight to bare metal silicon. Because at this level, time isn't measured in API calls or container schedules anymore. We're talking about pure processor clock cycles. Enter the Kronor RSIV processor. This is a 3-stage, in-order core that completely complies with the RV32i unprivileged architecture. What really makes this implementation stand out is how intensely optimized it is for FPGA hardware. It's explicitly engineered to hit single-cycle instruction execution while barely making a dent in the FPGA's lookup tables or LUTs. The payoff for all that optimization? Extreme efficiency. When running on the KRZ system on chip, this core hits 0.7105 DMIPS per megahertz. To pull off that level of processing density on an FPGA implementation constrained to just over 5,000 LUTs is a massive win for predictable, low-level execution. You can really see the predictability of this pipeline when you look at the CPI per instruction, or CPI, across different single-thread algorithm tests. Whether it's sorting data with QSort or running vector additions, that CPI stays incredibly consistent, hovering right between 1.6 and 1.9. When you're designing a bare metal core where timing is literally everything, that kind of stability is exactly what you want. taking a massive step up from a single FPGA to sprawling hardware clusters. We have another tool, this one developed by the European Center for Medium-Range Weather Forecasts, to simulate high-performance computing workloads. The workflow they built is fascinating. It pulls in profiled data from a real HPC system, builds a synthetic mathematical model of that schedule, and then deploys portable synthetic applications back onto the target hardware just to benchmark the execution efficiency. It is literally a tool built to model and optimize exactly how massive computer clusters spend their time. Which brings us to our final stop, the absolute theoretical bedrock of system architecture: fault-tolerant event ordering at scale. If you have thousands of independent machines running concurrently, how on earth do you get them to agree on what happened first? Researchers at the University of Waterloo built a service, yes, also called Kronor, to tackle exactly this. Their main thesis is that tracking dependencies shouldn't be a job for individual distributed subsystems. Instead, you need to pull that happens before graph out into a dedicated service. That gives you one unified global view of dependencies across the entire highly concurrent system. Here is how they actually abstract time in this system. It starts with event creation, where every state change gets a globally unique identifier. Then comes dependency assignment, where the system establishes pairwise time orders between events to build out the timeline. Finally, you have graph traversal, which allows clients to rapidly query causal relationships, even if those queries have to span across multiple server shards. Now, to make this work in the real world without completely freezing up the system, they came up with a brilliant way to handle batch ordering. They split dependencies into two types. First, you have must edges, which are your strict non-negotiable time dependencies. But then they added prefer edges. These are conditional operations. They prioritize an order, but if enforcing it would cause a conflict, they let it slide. This gives programmers a huge amount of control, avoiding impossible mathematical bottlenecks while keeping the database perfectly serializable. So whether we're quantizing massive financial markets, scheduling Kubernetes, squeezing every ounce of efficiency out of a RISC-V processor, or untangling millions of distributed events, the core challenge is exactly the same. As we continue to abstract away our infrastructure and push the absolute limits of scale, we have to ask ourselves, is time the ultimate bottleneck in distributed execution? Because understanding how to control it is clearly the key to whatever comes next.